What's up everybody, Adele here. Today's video is a collection of course videos from our OpenAI API Fundamentals skill track. Throughout the videos, you'll learn how to use the OpenAI API, learn about embeddings, how to use the OpenAI API to build systems, as well as prompt engineering best practices. Now, of course, these are only the videos from the courses, so if you want to actually practice your skills and practice in the browser, make sure to sign up to the skill track in the link in the description below. And with that, happy learning.
Welcome to the course. I'm James, and I'll be your host as we explore the artificial intelligence functionality available via the OpenAI API. In this course, you'll learn how to use the AI models available through the OpenAI API to solve a wide range of real-world tasks. To do this, we'll be using Python code throughout the course, and expect familiarity with a few Python programming topics, like subsetting lists and dictionaries, control flow, and looping. However, no experience with AI or machine learning is required. With that, let's dive in. OpenAI is a company that researches and develops artificial intelligence systems. One of their most famous developments is ChatGPT, which is an application that allows users to communicate with an AI-powered chatbot, to ask questions, perform tasks, or generate content. The OpenAI API allows individuals or organizations to access and customize any of the models developed and released by OpenAI. If OpenAI was a car manufacturer, ChatGPT would be their shiny new sports car that people can walk into a dealership and test drive. The OpenAI API would be like the system customers could use to customize and order cars from the manufacturer's catalog. So what actually is an API? API stands for Application Programming Interface, and they act as messengers between software applications, taking a request to a system and receiving a response containing data or services. APIs are like waiters in a restaurant. They take our order or request, communicate it to the kitchen, the system providing the service, and finally deliver the food or response from the system back to our table. Many applications interact using APIs. For example, a mobile weather app may send our location to an API and request the local weather forecast, which is returned back to our phones. Similarly, we can write code to interact with the OpenAI API and request the use of one of their models. Our request in this case will specify which model we want, the data for the model to use, and any other parameters to customize the model's behavior. The response, containing the model result, is then returned. Some of OpenAI's models can be used from the web browser, such as via ChatGPT. This low setup browser experience is often sufficient for streamlining our workflows using AI. However, if we're looking to begin integrating AI into our products, customer experiences, and business processes, we'll need the flexibility of working with the models programmatically using an API. The OpenAI API has enabled the development of powerful new features that before would have required enormous computational resources and data. In this example from DataLab, DataCamp's own AI-powered IDE, we developed a feature where you can use natural language to extract insights from data, all built on the OpenAI API. I highly recommend giving it a try. Welcome back. Let's learn how to make requests to the OpenAI API. Depending on the model or services required, APIs have different access points for users, called endpoints. Endpoints are like doors in a hospital. Depending on the treatment required, patients use different doors to reach different departments. And likewise, users make requests for different services to different API endpoints. Endpoints, like many hospital departments, may also require authentication before accessing services. API authentication is usually in the form of providing a unique key containing an assortment of characters. It's important to note that many APIs, including the OpenAI API, have costs associated with using their services. For OpenAI, these costs are dependent on the model requested and on the size of the model input and output. But don't worry. In this course, we've configured the exercises in such a way that you don't need to pay anything to make requests to the OpenAI API. In this course, creating an API key for authentication isn't required. But if you'd like to create one for other projects, you need to create an OpenAI account, go to the API keys page, and create a new secret key. OpenAI sometimes provides free trial credit to new users, but if not, you may need to add some credit. There are several ways to interact with an API, but in this course, we'll use OpenAI's own Python library. We start by importing the OpenAI class from OpenAI, which we'll use to instantiate an OpenAI API client. The client configures the environment for communicating with the API. Inside, we specify our API key. In this course, this will be filled out for you. Now for the request code. We'll start by creating a request to the chat completions endpoint by calling the create method on client.chat.completions. The chat completions endpoint is used to send a series of messages representing a conversation to a model, which returns a response. Inside this method, we specify the model and the messages to send. The messages argument takes a list of dictionaries, where content sent from the user role allows us to prompt the model. Here we prompt the model to define the OpenAI API. We'll discuss roles and their uses in much more detail in the next chapter. Let's take a look at the API response. There's a lot here, so we'll add additional spacing to improve readability. The response from the API is a chat completion object, which has attributes for accessing different information. It has an ID attribute, choices, created, model, and other attributes below. We can see that the response message is located under the choices attribute. So we'll start by accessing it. Attributes are accessed using a dot, then the name of the attribute. We've gotten much closer to the text. Notice from the square brackets at the beginning and end that this is actually a list with a single element. Let's extract the first element to dig deeper. Okay, we're left with a choice object, which has its own set of attributes. The message is located underneath the message attribute, which we can chain to our existing code. Almost there. Finally, we need to access the chat completion message's content attribute. There we have it. Our model response is a string. We started off with a complex object, but by taking it one attribute at a time, we were able to get to the result. In this chapter, we'll take a deeper dive into the capabilities of OpenAI models available via the API. So far, we've used the chat completions endpoint to answer general knowledge questions, but the model's capabilities go far beyond this. To understand where these capabilities come from, let's discuss how these models generate text. When we send a prompt to the chat completions endpoint, the model returns the text that it believes is most likely to complete the prompt, which it infers based on the data the model was developed on. If we send "life is like a box of chocolates" to the model, it correctly completes the quote with high probability. We say high probability here because the model results are non-deterministic, so we cannot guarantee consistency in the model outputs. There are many use cases where randomness is undesirable. Think of a customer service chatbot. We wouldn't want the chatbot to provide different guidance to customers with the same issue. However, we would like the model to be flexible to different inputs, so there's often a trade-off in the amount of randomness. We can control the amount of randomness in the response using the temperature parameter. Temperature is set to 1 by default. but ranges from 0 to 2, where 0 is almost entirely deterministic and 2 is highly random. If we add a temperature of 2 here, we can see the model completes the prompt in a more bizarre way. Because these models return the most likely text to follow the prompt, they can be used to solve a number of tasks besides answering questions, including generating and transforming text. Text transformation includes tasks such as find and replace, summarization, and copy editing. For example, we can use the API to update the name, pronouns, and job title in a biography. Notice that the prompt starts with the instruction, then the text to transform. We've also used triple quotes to define a multi-line prompt for ease of readability and processing. Then, as before, we send this prompt to the chat completions endpoint. Voila! We have our updated text. Even with a find and replace tool, this task would normally require us to specify each word and its replacement. Text completions are also used to generate new text content from a prompt providing an instruction. For example, we can create a request to generate a tagline for a new hot dog stand. That's pretty good. By default, the response from the API is quite short, which may be unsuitable for many use cases. The max tokens parameter can be used to control the maximum length of the response, shortening or lengthening it. Tokens are a unit of one or more characters used by language models to understand and interpret text. Here we can see how the model would encode this sentence as tokens to process it on input. Recall that the API usage costs are dependent on the model used and the amount of input and output text. Each model is actually priced based upon the cost per number of tokens, where input and generated tokens can be priced differently. So increasing max tokens will likely increase the usage cost for each request. When scoping the potential cost of new AI features, the first step is often a back-of-the-envelope calculation to determine the cost per unit time. So we've seen that OpenAI's models are pretty flexible and can do much more than answer questions. In this video, we'll take this a step further to discuss classification tasks. Classification tasks involve assigning a label to a piece of information. This can be identification, such as identifying the language used in a piece of text, categorization, such as sorting geographical locations into countries and US states, or even classifying a statement's sentiment, that is, the emotions behind it. OpenAI's models can be used for all of these tasks, providing the model has sufficient knowledge of the subject area and that the prompt contains the necessary context. Let's use the chat completions endpoint to categorize these animals. Printing the response, we can see that the model categorized the animals into mammals, fish, and reptiles. This might be what we were looking for, but there's an almost infinite number of ways to categorize, so it's better to state the desired categories in the prompt. We can update the prompt to categorize animals into those with and without fur, and the model responds with the desired categories. Let's look at an example of classifying text sentiment. Let's say we have some online restaurant reviews, and we want to extract the sentiment for further analysis. We can write a prompt with the instruction to classify sentiment from a list of statements, and then send it to the chat completions endpoint and print the response. The model does a good job. However, rather than a text sentiment like positive and negative, we decide we want the category labels to be the numbers 1 to 5. We can update our prompt to indicate this. The response now contains a reasonable numerical representation of each review sentiment. The prompts we've used so far are examples of so-called zero-shot prompts, where we haven't provided any examples in the prompt for the model to learn from. For cases where the model may not have a good understanding of the subject matter or task, we may need to provide some examples for it to learn from. If one example is provided in the prompt, it's called one-shot prompting, and for multiple, it's called few-shot prompting. One-shot and few-shot prompting are examples of in-context learning techniques, when the model learns from the context we're providing. Let's return to sentiment analysis to give these prompting techniques a go. We're again dealing with restaurant reviews, but this time we want the sentiment to be more specific. To do this, we provide one example in the prompt, clearly separating the input and output, followed by the review to analyze. Sending this to the chat completions endpoint and printing the result shows that the model was able to grasp that we wanted more specific category labels. In more complex cases, one example is not enough, and we'll need to experiment to determine the number of shots the model needs. Let's extend the prompt to provide 3 examples. Running the same code again, we see that adding the extra examples didn't noticeably improve the output quality this time. Welcome back. In this video, we'll learn to unlock the chat capabilities from the OpenAI API, which underpin popular applications like ChatGPT. Let's get started. So far, we've used the chat completions endpoint to perform a number of tasks, including text generation and transformation, and classification tasks like sentiment analysis. These are so-called single-turn tasks, as there's one input and one output. With chat completions models, it's possible to also have multi-turn conversations, so we can build on our previous prompts depending on how the model responds. Roles are at the heart of how chat models function. Up until this point, we've only used the user role, but there are also system and assistant roles. The system role allows us to specify a message to control the behavior of the assistant. For example, for a customer service chatbot, we could provide a system message stating that the assistant is a polite and helpful customer service assistant. The user role is used to provide an instruction to the assistant, and the assistant role is attached to model responses. Interestingly, we, the user, can provide these system messages, which are often utilized to provide example responses to help the model understand the desired output. We'll discuss multi-turn conversations in the next video. For now, we'll get familiar with using chat roles for single-turn tasks. Here's a typical chat completions request that we've used for single-turn tasks. We've passed the messages argument a list containing a dictionary with role and content keys, which has been a prompt sent from the user role. To include additional messages, we extend the list to include multiple dictionaries, each with their own role and content. These messages often start with the system role, which here instructs the assistant to act as a data science tutor that speaks concisely. Let's add these messages into the request code and print the response text using the same combination of attributes we've used previously. Great work so far. In this video, we'll begin to unleash the full potential of chat models by creating multi-turn conversations. Recall that messages are sent to the chat completions endpoint as a list of dictionaries, where each dictionary provides content to a specific role from either system, user, or assistant. For single-turn tasks, no content is sent to the assistant role. The model relies only on its existing knowledge, the behaviors sent to the system role, and the instruction from the user. Providing assistant messages can be a simple way for developers to steer the model in the right direction without having to surface anything to end users. For a data science tutor application, we could provide a few examples of data science questions and answers that would be sent to the API along with the user's question. Let's improve our data science tutor by providing an example. Between the system message and the user's question, We'll add a user and assistant message to serve as an ideal example for the model. The model now not only has its pre-existing understanding, but also an ideal example to guide its response. With an example to work with, the assistant provides a response in line with the example. Another common use for providing assistant messages is to store responses. Storing responses means that we can create a conversation history, which we can feed into the model to have conversations. This is exactly what goes on underneath AI chatbots like ChatGPT. To code a conversation, we'll need to create a system so that when a user message is sent and an assistant response is generated, they are fed back into the messages and stored to be sent with the next user message. Then, when a new user message is provided, the model has the content from the conversation history to draw from. This means that if we introduce ourselves in the first user message, then ask the model what our name is in the second, it should return the correct answer, as it has access to the conversation history. Let's start to code this in Python. We start by defining a system message to set the assistant's behavior. You can also add user assistant example messages here if you wish. Then we define a list of questions. Here we ask why Python is popular, and then ask it to summarize the response provided in one sentence, which requires context on the previous response. Because we want a response for each question, we start by looping over the user questions list. Next, to convert the user questions into messages for the API, we create a dictionary and add it to the list of messages using the list append method. We can now send the messages to the chat completions endpoint and store the response. We extract the assistant's message by subsetting from the API response, converting to a dictionary so it's in the messages format, then add it to the messages list for the next iteration. Finally, we'll add two print statements, so the output is a conversation between the user and assistant written as a script. We can see that we were successfully able to provide a follow-up correction to the model's response without having to repeat our question or the model's response. Up to this point, we've used OpenAI's models for completing text in some way, whether it's answering questions, classifying statements, or editing text. In this chapter, we'll go further into the API's capabilities, including text moderation, audio transcription and translation, and even combining models together. Let's start with text moderation. Text moderation is the process of identifying text that is inappropriate for the context in which it is being used. In online communities like social networks and chat rooms, moderation is crucial to prevent the exchange of harmful and offensive content. Traditionally, this moderation was done by hand, where a team of moderators flagged the content that breached usage rules. More recently, this was done by algorithms that detected and flagged content containing particular keywords. Manual moderation is extremely time-consuming, and if multiple moderators are involved, introduces a subjective element that may result in inconsistencies. Keyword pattern matching, although much quicker and able to run round the clock, can be a clumsy tool that misses some malicious content while accidentally flagging perfectly good content, because it doesn't understand nuance or the context of the discussion. To prevent the misuse of their own models, OpenAI have developed moderation models to flag content that breaches their usage policies. The OpenAI moderation models can not only detect violations of their terms of use, but also differentiate the type of violation across different categories, including violence and hate speech. To create a request to the moderations endpoint, we call the create method on client.moderations and specify that we want the latest moderation model, which often performs the best. If a use case requires greater stability in classifications over time, we can also specify particular model versions. Next is the input, which is the content that the model will consider. This statement could easily be classed as violent by traditional moderation systems that work by flagging particular keywords. Let's see what OpenAI's moderation model makes of it. We'll dump the response to a dictionary for easier readability. The output is similar to other endpoints. There are three useful indicators that can be used for moderation. Categories, representing whether the model believed that the statement violated a particular category. Category scores, an indicator of the model's confidence of a violation. And finally, flagged, whether it believes the terms of use have been violated in any way. Let's extract the category scores from the response for a closer look. The category scores are float values for each category, indicating the model's confidence of a violation. They can be extracted from the results attribute, and through that, the category scores attribute. The scores can be between 0 and 1, and although higher values represent higher confidence, they should not be interpreted as probabilities. Notice from the small numbers, including in the violence category, that OpenAI's moderation model did not interpret the statement as containing violent content. The model used the rest of the sentence to interpret the context and accurately infer the statement's meaning. The beauty of having access to these category scores means that we don't have to depend on the final true-false values outputted by the model. We can instead test the model on data from our own particular use case and set our own thresholds based on the results. For some use cases, such as student communications in a school, strict thresholds may be chosen that flag more content, even if it means accidentally flagging some non-violations. The goal here would be to minimize the number of missed violations, so-called false negatives. Other use cases, such as communications in law enforcement, may use more lenient thresholds, so reports on crimes aren't accidentally flagged. Incorrectly flagging a crime report here would be an example of a false positive. Welcome back. We're now going to move away from OpenAI's text models to take a look at the functionality of their audio models. OpenAI's Whisper model has speech-to-text capabilities that can be used to create audio transcripts or translate audio from one language into an English transcript. The model supports many of the most common audio file formats, but does place a limit on the size of the audio file. Whisper has potential applications in automating transcripts, as well as accessibility features like caption generation. In this video, we'll discuss creating transcripts. Let's use Whisper to transcribe a meeting recording stored in an MP3 audio file. The first thing we need to do is load the file into our Python environment. There are lots of Python libraries out there for working with audio files, but we'll be using the Python open function here. The open function takes two arguments. The first is the file to be opened, and the second indicates the mode with which the file should be opened. Different modes support reading and writing to virtually any file type. The RB here stands for read binary. All this means is that we're opening a file that is stored in a binary format, which is typical for non-text files like audio, video, and images. If the audio file is stored in a different directory to the Python script or notebook we're working in, we also need to prepend the file name with its path. This audio file can now be used like any other Python variable. Requests to the Whisper model are sent to the audio endpoint of the API. To create a transcription request to this endpoint, we call the create method on client.audio.transcriptions. Inside, we specify the audio model to use and the audio file to transcribe. Let's print the response to see what's returned. Like the other endpoints, we receive an object with attributes, but fortunately for transcriptions, there's only a single attribute to handle. We can access the transcript text using the text attribute. There we have it. The model did a solid job of transcribing the audio, but note that its performance may fluctuate with changes in audio quality or different accents. Sensitive or confidential audio should also not be sent to the model. Due to the Whisper model being trained on audio from non-English languages, it can also transcribe audio from many other languages with good results. The process for transcribing non-English audio is exactly the same. We open the audio file, make a transcription request to the audio endpoint, and extract the text from the response. In this video, we'll discuss Whisper's translation capabilities. Let's dive right in. The Whisper model not only has the ability to transcribe audio into the language it's in, but also translate and transcribe audio in one go. This is currently limited to an English transcript, so we can translate and transcribe German into English, but not German into French. Like with its transcription functionality, Whisper can translate audio from most common audio file types, up to a particular size limit. The process for translating and transcribing audio is almost identical to normal transcription, with just one change. We open the non-English audio to translate and transcribe, which in this case is an M4A file. This is where the change comes in. Instead of calling the create method on client.audio.transcriptions, we call it on client.audio.translations. The translated transcription can be extracted using the text attribute. Looking at the transcript, we can see that it wasn't perfect, making 2 spelling errors. The performance of Whisper can vary wildly depending on audio quality, the language the audio is recorded in, and the model's knowledge of the subject matter. Before creating a full-fledged application on this model, you'll need to test that the model's performance is sufficiently good for the particular use case. Let's see how we can give Whisper a helping hand here. When we send our audio to the Whisper model, we can also provide an optional prompt. This prompt can be used to improve the quality of the response by providing an example of how we want the transcript to be styled. For example, if we want the transcript to retain filler words from the audio, like ums and ers, we can provide the following prompt along with the audio. If we know broadly what the topic of the audio is about, we can also provide this context as a prompt to help the model narrow down the correct words. Here's an example of a prompt to give the model more context. Transcriptions also supports prompts in a very similar way. Let's adapt our last request with a prompt to try and fix the spelling errors outputted by the model. Let's assume that we know the audio discusses AI trends and ChatGPT. We can define a prompt with this context and pass it to the prompt argument. Printing the response shows that, with a little extra context, the model was able to accurately determine the correct spelling and style of the words. In this example, the original response was already pretty close to what we wanted, but for other cases, it's possible to see quite dramatic improvements using prompts.
Welcome back. In this video, we'll take it up a gear and look at how we can combine models together. So far, when we've been using functionality from the OpenAI API, we've completed a task by passing an input to the model and receiving an output. This got us pretty far, from simple question answering to multi-turn conversations and audio translation. But what if we could do more with the model's output? Enter model chaining. Chaining is when models are combined by feeding the output from one model directly into another model as an input. We can chain multiple calls to the same model together, or use different models. If we chain 2 text models together, we can ask the model to perform a task in one call to the API, and send it back with an additional instruction. For example, let's say we draft an email template for a customer, and we want to validate that the template follows some guidelines. We can send it back to the model with an instruction to check whether the guidelines are followed. We can also combine 2 different types of models, say the Whisper model into a text model, to perform tasks like summarizing discussion points and next steps from a meeting recording. Let's have a go at chaining Whisper with a chat model. Let's use Whisper to extract the attendees from a meeting recording, where we know it starts with introductions from each of the attendees. We start by opening the audio file and assigning it to audio_file. Next, we send the audio to the Whisper model and request a transcript with the transcribe method. To extract the transcript from the response, we extract the value from the text key. Now that we have the meeting transcript, we can use it to create a prompt for the chat model. The prompt starts with an instruction to extract the attendee names from the start of the transcript. Then we append the transcript to the end. We're now ready to send the prompt to the chat model. We create a request to the chat completion endpoint using the create method. Inside, we specify the model to use and the messages to send, which is just the prompt in this case. Finally, we extract the response from the chat model. And there we have it. As with all of these models, there's no guarantee that the models will be 100% accurate. Whisper could make a mistake in the transcript, or the chat model may summarize incorrectly. It's important that any application of these models is well tested, iterating on the prompts if necessary, to understand its performance thresholds. Additionally, usage should be restricted to only non-sensitive data, as we may risk breaching data governance laws by unjustly exposing employee or customer data.
Welcome to this course. I'm Fuad, and I'm a machine learning engineer working on leveraging AI to improve cybersecurity. I'll guide us through prompt engineering techniques to maximize ChatGPT's capabilities. Let's dive in. What is prompt engineering? Prompt engineering refers to crafting prompts or instructions given to large language models or LLMs to get desired responses. Prompt engineering is like whipping up a recipe for a meal. Just as a chef picks out the right ingredients and mixes them together to create something delicious, prompt engineering involves carefully crafting prompts to steer the model toward the desired outputs. And just as high-quality ingredients lead to high-quality meals, in prompt engineering, high-quality prompts lead to high-quality answers, and low-quality prompts lead to low-quality answers. In this course, we'll explore various prompt types and applications using the OpenAI Python package to test our prompts. The package allows to interact with the OpenAI API programmatically using a key. Creating an API key isn't required to complete this course, but you can create your own key if you'd like to have it for future work. Various endpoints can be accessed through the API, but the main one used for chatting is chat completions. Every API message has one of the three roles: user, assistant, or system. System messages provide instructions to guide the model's behavior throughout a conversation. User messages are prompts from the user, and assistant messages are the responses to user prompts. Recall that the API has helpful control parameters. One of these is temperature, a value between 0 and 2 that controls the randomness of the answer. 2 makes the answer highly random and 0 makes it deterministic. Another parameter is max tokens, which controls the desired response length. To ask what is prompt engineering via the API, we set up the client by calling the OpenAI class and setting the API key. Then, we call the chat.completions.create function, specifying the model and messages as a list of dictionaries with the role and content. We set the temperature to 0 for deterministic answers and do not specify max tokens to allow full responses. Finally, we print the response. We will use this code block a lot for API communication throughout the course. To avoid writing it every time, we wrap the code inside a function named getResponse that takes a prompt as input and sends it to the API just as before. Instead of printing the response, the function returns it as output. Now, we can call this function with one line of code and save the returned value in a variable we can print. Prompt improvement now becomes a matter of modifying the prompt we're giving to the function. For instance, we can modify our previous prompt to let the model explain prompt engineering in terms that a 5-year-old can understand. The new response is written using more basic vocabulary and compares prompt engineering to giving clear instructions to a friend. Now we'll dive into the key principles of prompt engineering to create more effective prompts. When interacting with an LLM, we aim for clear and precise prompts to achieve the best results. This is like guiding someone from one location to another by choosing the simplest and most effective path. We'll explore 3 principles of prompt engineering, including the use of appropriate action verbs, detailed and precise instructions, and well-structured delimited prompts. When asking the model to perform certain tasks, opt for action verbs that explicitly guide the model's task, such as write, complete, explain, describe, or evaluate. Conversely, avoid using ambiguous verbs like understand, think, feel, try, and know, which might confuse the model's understanding. A prompt asking the model to think about deforestation is ineffective. While the model generates some output, it remains vague and the prompt needs greater clarity on what is being asked. For example, we can use an action verb to guide the model to a specific task, proposing strategies to reduce deforestation. When crafting prompts, we'll want to provide specific, descriptive, and detailed instructions about context, output length, format, style, and audience. A prompt asking to tell us about dogs is too broad. However, when we ask for a description of the behavior and characteristics of golden retrievers, we get a more precise answer with the details we've requested, including characteristics and suitability for families. Another key principle for writing effective prompts is to specify the structure of the result, giving indications on how many paragraphs, sentences, or words we aim to generate. To limit output length, we can use the max tokens parameter, which enforces a strict token limit but may result in incomplete responses. Specifying limits in the prompt, such as maximum words, sentences, or paragraphs, can be bypassed but ensures complete responses. A prompt might contain instructions and some input data to operate on. For example, in text summarization, the instruction would be to summarize a given text, and the input provided would be the text that needs to be summarized. To craft a well-structured prompt, place instructions at the beginning, use delimiters like parentheses, brackets, or backticks for input parts, and specify the delimiters used. This helps the model locate the input. In this example, we use triple backticks to delimit the input text for summarization. Instead of including long inputs within the prompt string, we can use Python's f-strings to embed a predefined string. In this example, we define the variable text, add an f before the prompt string, and place the text variable in curly brackets inside the prompt. This incorporates the variable's content into the prompt. We'll be frequently using this format in the course. In this video, we will focus on creating structured outputs and using conditional prompts. Language models don't naturally generate structured outputs without explicit instructions. However, sometimes we need the output in a table, list, structured paragraph, or custom format. Let's see how to handle these cases. To generate a table, we should clearly mention the expected columns. For example, to instruct the model to create a table with 5 action movies, we specify the columns title and rating. This ensures the output meets our requirements. A list is another format, helpful for enumerations. For example, if we ask the model to generate a list of the top 5 cities to visit, the output will be a numbered list of cities. We should explicitly mention specific requirements for how the output list should be formatted in the prompt. If we ask the model to generate an unordered list, the output will not be numbered. To get structured paragraphs, we should explicitly mention format requirements in the prompt. For example, here we ask the model for a paragraph with clear headings and subheadings about the benefits of exercising. We see how the output is formatted with 3 headings: Introduction, Physical Health Benefits, and Mental Health Benefits, along with additional subheadings. When a custom output format is needed, one approach is to break down the prompt into parts. Here, we define an input text, such as the opening of a fairy tale about a boy named David. We then instruct the model to generate an appropriate title and specify the output format for the text and title. We combine the instructions, output format, and input text in the final prompt. This ensures the output meets our requirements, providing a title for David's adventures with the original text in the requested format. Sometimes we might want to incorporate some logic or conditions in our prompts. In this case, we use conditional prompts with an if-else structure. If a condition is true, perform X. Otherwise, perform Y. Suppose we want the model to suggest a title for some provided text, but only if the text is in English. To do that, we explicitly mention this condition in the prompt. If the text is in another language, we tell the model to inform users that it only understands English. Now, for a French text describing my favorite season, the output will be "I only understand English." We can incorporate multiple conditions in our prompt. For instance, we might tell the model to generate titles only for English texts containing the keyword technology. If the text is written in English, we check if it contains the keyword. If it does, the model suggests a title. Otherwise, it responds with keyword not found. Non-English texts are treated just as before. Now, for a paragraph describing a forest, the model tells us that the keyword was not found. Welcome back! In this video, we'll explore few-shot prompting techniques and their applications. Let's get started. Few-shot prompting involves giving language models examples within the prompt. We create a prompt with example question-answer pairs and the question we want the model to answer. We feed this prompt to the model, and we get the answer to our question in return. With this approach, the model learns how to answer the given question from the examples. The name of the technique varies depending on the number of examples we provide. When 0 examples are provided, we are using zero-shot prompting. 1 example is one-shot prompting. More than 1 example is few-shot prompting. Let's explore each in detail. In zero-shot prompting, the model gets a prompt without examples and responds based on its existing knowledge. This is ideal for quick, simple tasks. For instance, we can use zero-shot prompting when asking the model to define prompt engineering without giving examples. In one-shot prompting, we provide one question-answer example, helping the model learn a specific format or style. This is useful for consistent outputs. For instance, to sum numbers in a specific format, we give an example like 3 plus 5 plus 6 equals 14, and the model will follow this style for new sums. We can use one-shot prompting to guide the model to structure the answer in a specific way. Let's use the same prompt and example, but with the output being a sentence like "the sum of 3, 5, and 6 is 14. The response to our second question now follows the same format. In few-shot prompting, we give the model multiple examples. This is useful for complex tasks requiring more context. For instance, for sentiment analysis, we provide sample texts with their classifications, and the model uses the categories to classify new texts. We can provide examples as previous conversations in the chat completion function. For sentiment analysis, we send the text as a user message and the class as an assistant message. We do this for all examples and finally send the text to classify as a user message without the assistant message and print the output. When using few-shot prompting, consider the task's complexity to select the optimal number of examples. Fewer examples can handle basic tasks like using one example to control output structure. For more complex tasks like multi-category text classification, we should provide diverse examples, ensuring at least one for each class to guide the model effectively. Let's explore multi-step prompting, which guides the model's behavior to generate effective outputs. Multi-step prompting breaks down a goal into smaller steps, guiding the model through each step to improve accuracy. This technique benefits sequential tasks like generating coherent text from an outline, which need ordered steps. Cognitive tasks such as evaluating a solution's correctness also utilize multi-step prompts as they involve problem-solving and decision-making processes. We can think of multi-step prompts as treasure maps. They break down a complex task into smaller, manageable steps, guiding the model to the desired outcome through a sequence of clues and directions. Suppose we want to write a travel blog. We might start with a single-step prompt asking the model to create the entire blog without additional details. In this example, the model will generate text about a random journey through Iceland with a day-by-day itinerary. For more detailed content, we use a multi-step prompt. We ask to introduce the destination, share personal adventures, and summarize the journey. We don't ask for a specific destination as we'd like to focus on the blog structure. The model generates a coherent travel blog sequentially according to our instructions, with an introduction to Barcelona, an adventure, and a summary. Multi-step prompting can also be used for cognitive tasks like checking whether code is correct. For example, for analyzing the correctness of Python code computing basic calculations such as addition, subtraction, multiplication, and division. Here, the calculator string contains the file's content we want to verify. It includes functions that accept two numbers as input and perform addition, subtraction, multiplication, or division, returning the results. As a starting point, we may start with a single-step prompt asking the model to assess the code's correctness. However, a simple yes doesn't explain the evaluation. We may need specific criteria or domain knowledge to refine the evaluation. In this case, while the syntax is correct, the divide function doesn't handle division by zero, which should be considered in the evaluation. To accomplish that, we use a multi-step prompt, where in step 1, we check for syntax correctness, and in step 2, we verify if division by zero is handled. After these changes, the model output gives feedback about each step and tells us the syntax is correct, but division by zero is not handled. Let's review the differences between multi-step and few-shot prompts. While both steps and shots play crucial roles in controlling the model's behavior, steps are instructions that explicitly tell the model what to do. They act as a roadmap for the model by providing specific guidance. Shots are example questions and answers that the model learns from. They demonstrate how the model should respond to certain inputs. The model observes these examples and learns to generalize from them. In this video, we will discuss prompting techniques to understand the output a model returns. Chain of thought prompting requires language models to present reasoning steps or thoughts before giving a final answer. This technique is valuable for complex reasoning tasks and helps reduce errors by processing the reasoning step by step. To understand the power of chain of thought prompts, let's compare them with standard prompts using a math problem. Suppose we want to determine how many books a person has given their existing count and their lending and purchasing decisions. A standard prompt gives us a number but doesn't explain the reasoning. We can verify its correctness without seeing the steps taken. To address this, use a chain of thought prompt asking the model for a step-by-step explanation. The model solves the problem as a series of 5 steps, providing the correct answer. We can use few-shot prompts to obtain chain of thought reasoning. Instead of instructing the model to generate reasoning steps, we provide examples of what the answers should include. For instance, to determine if a group of odd numbers adds up to an even number, we provide an example question and answer. This exemplifies the steps: finding the odd numbers first, then summing them to verify the statement. We then provide a new question with an A for the model to answer. We combine the example and the question to obtain the final prompt. As a result, the model follows a similar logic in its response. Let's study the difference between multi-step and chain of thought prompts. With multi-step prompts, the various steps of the task are directly incorporated into the prompt itself, guiding the LLM's behavior. Chain of thought prompts take a different approach by instructing the model to generate intermediate steps or thoughts in its output as it solves the problem. This helps gain insight into the model's decision-making. One limitation of chain of thought prompting is that one thought with flawed reasoning will lead to an unsuccessful outcome. This is where self-consistency prompts come in. Self-consistency prompting is a technique that generates multiple chain of thought responses by prompting the model several times. The final output is determined by a majority vote, selecting the most common response as the result. To implement self-consistency prompting, we can define multiple prompts, or a prompt where the model imagines several independent answers. Here, we ask for several independent experts to solve a mathematical problem determining the number of cars in a parking lot, with the final answer obtained by majority vote. To obtain the final prompt, we combine this instruction with the mathematical problem to solve. In the output, the model gives the response from each expert and aggregates the result to provide a final answer. Since 2 of the 3 experts obtained the number 12, the final answer is 12. Let's explore iterative prompt engineering and refinement, a paradigm that can be applied to any type of prompt we previously covered. Even with the many techniques we have learned, prompt engineering doesn't always succeed on the first try. It is an iterative process where we build a prompt, feed it to the model, observe and analyze the output, and accordingly reiterate to make the prompt better. Sometimes we must refine our prompt because the model misunderstands the request. For example, asking it to generate an Excel sheet with 5 students' names and grades might prompt it to create an actual Excel file, which it can't do. Refining the prompt to ask for a table that we can copy into Excel gives us a better output. Prompt refinement can also help tailor responses to our requirements. Let's illustrate this by analyzing a Python function that calculates the area of a rectangle given its length and width. We start with a prompt asking the model to analyze the code in one sentence. The output correctly states the code calculates a rectangle's area given its length and width. However, we wanted more details, like the programming language used. In this case, we need to iteratively refine the prompt. We modify the initial prompt to ask explicitly for the programming language, and accordingly the model mentions that the function is written in Python. Now, suppose we want to get structured information about the function, like a short description, the programming language, the inputs, and the outputs. We explicitly mention this in the prompt and feed it to the model. The output incorporates all the elements we requested in our refined prompt. Iterative prompt engineering isn't limited to standard prompts. For example, to classify weather descriptions using a few-shot prompt, We provide sample weather descriptions with classifications and a new description for the model to classify. As we can see, the model accurately classifies it as snowy even without prior examples of snowy. But what happens if we want to classify a description stating the wind of change brought a refreshing breeze to the company's operations? The model mistakenly classifies it as windy despite not being related to weather at all. To refine the few-shot prompt, we refine its examples. In this case, we add one example stating the political climate in the country was stormy and assign it to the class unknown. The model correctly classifies the previous description as unknown. It's been provided with enough information to classify such cases. Prompt refinement applies to all prompt types. We refine examples in few-shot prompts, guiding steps in multi-step prompts, and problem descriptions in chain of thought and self-consistency prompts. The model may generate incorrect responses due to a lack of domain knowledge, which we will address in later chapters. Great work so far! Now that we're comfortable with prompt engineering principles and strategies, let's apply this knowledge to business applications. This video will focus on developing effective prompts for text summarization and expansion. Text summarization condenses text into a shorter, coherent version while preserving its essential meaning. This technique is used across industries to streamline business processes. In finance, it speeds up decision-making by summarizing lengthy reports. In marketing, it turns customer feedback into actionable insights for better campaign strategies. If prompted effectively, language models can be leveraged for summarization. Summarizing text can seem straightforward, providing the model with text and asking to summarize it. For example, here we have a smartwatch review covering design, quality, and comfort. If we ask the model to summarize it using a simple prompt without details, the model will do so, but the prompt could be more effective with specific guidance. We can specify the output limits, output structure, and summarization focus to make the prompt more effective. We can specify the output limits by the number of sentences, words, or characters. Here, for the same smartwatch review, we modify the prompt to ask for one sentence, which we see reflected in the output. We can also specify the output structure by explicitly mentioning the format in the prompt. Let's try this by asking for 3 bullet points at most. Now, the output is a 3-bullet summary reflecting the qualities of the watch. Finally, we can ask the model to focus on specific aspects of the product review while summarizing. Here, we can instruct the model to summarize the review in 3 sentences, focusing on the key features and user experience. This helps us identify the product's strengths and drawbacks. As we can see, the response has precisely 3 sentences, highlighting the user's positive feedback and the key features they enjoyed about the product. Text expansion, the opposite of summarization, generates text from a few ideas or bullet points. It boosts business efficiency and productivity by streamlining communication and reducing time spent on tasks like composing emails or generating report text. With LLMs, we can effectively expand text when using well-crafted prompts. A typical text expansion prompt should ask to expand a delimited text, highlighting key focus areas and specifying output requirements like tone, length, structure, and audience. Let's illustrate text expansion with an example. We have bullet points describing a company's social media services, such as content creation and community building. To create a coherent description of their services, we use a delimited prompt to ask the model to expand the bullet points into a professional 2-sentence overview of its features and benefits. The model expands the service description to 2 sentences using a professional tone. Now, we will explore text transformation applications and how effective prompt engineering facilitates them. As the name suggests, text transformation changes a given text to create new text while maintaining the same information. Applications include language translation, tone adjustment, and writing improvement, all achievable with LLMs using effective prompts. Let's explore language translation first. When asking the LLM to translate a text, we should specify input and output languages in the prompt. For example, here we have an English product description for an electric scooter, and we ask the model to translate it to French. But what if the language of the input text is unknown? We can ask the model with a delimited prompt to name the language. Here, the text is written in German. We can translate text from one language to multiple languages simultaneously. Here, we ask the model to translate an English product review into French, Spanish, and German, and the model generates the requested translations. Companies may use LLMs for initial translations, but should verify accuracy, especially for customer-facing content. With tone adjustment, text is rewritten to suit various business needs. For instance, a marketing company might have an informal promotional message about its summer sales. We can ask the model to rephrase it more formally and with a persuasive tone by specifying this in the prompt. The text is now transformed into a professional invitation for customers to explore remarkable summer sales, highlighting unique benefits. The tone and structure are more formal and polished. To adapt a text's tone, we can specify the target audience, a key strategy in effective communication. For instance, a product description with technical jargon about microprocessors and algorithms can be rephrased for a non-technical audience. We can ask the model to rewrite it this way, making it more accessible to the target audience. Text transformation also includes grammar and writing improvements. To correct spelling, grammar, and punctuation without changing the structure, we can ask the model for proofreading. For instance, in this text inviting for collaboration, the model can correct typos and grammar mistakes without altering the style or the structure. However, if we want the model to enhance the clarity of our text by modifying its structure while retaining the same meaning, we should ask it to proofread and restructure the text for enhanced readability, flow, and coherence. In this case, using the same text with the spelling errors, we observe how the structure becomes more readable and well written. Finally, we can perform multiple transformations at once using multi-step prompts. Suppose we have the following text for a product review written informally with many errors. We ask the model to proofread it first, then rewrite it in a professional tone. The model corrects the text in step 1 and rewrites it in step 2. It's time to analyze text using effective prompts. Text analysis is the process of examining text to extract relevant information. This video explores text classification and entity extraction techniques using sample customer data. Note that these examples are fictional and companies should seek legal advice for using customer data in compliance with privacy regulations. In text classification, the goal is to assign one of several potential categories to a given text. A common example is sentiment analysis, which categorizes text as positive, negative, or neutral. To classify texts effectively, we should specify the classification categories and output requirements in the prompt. For instance, when asking the model to classify the sentiment of a smartwatch review, we explicitly mention the options as positive, negative, or neutral and request a one-word response. The model responds according to our specifications. When classification categories are not specified, the model relies on its internal knowledge. Using the previous prompt without defining categories will still work for standard sentiment analysis. However, for more complex cases, it's best to specify classes to ensure expected outcomes. Texts can fit multiple classes, such as a review expressing several emotions. Without a predetermined list, the best practice is to ask the model to specify a maximum number of classes when specifying emotions. For the smartwatch review, we instruct the model to list up to 3 emotions. The model identifies the customer as impressed, positive, and comfortable. Another form of analyzing text is through entity extraction, where the goal is to extract specific entities from a given text, including names, places, organizations, and dates. To extract entities effectively, we should specify the entities to extract and the desired output format. Here, we have a product description for a mobile phone, and we instruct the model to identify the product name, display size, and camera resolution while formatting the answer as an unordered list. We see how the model extracts the product name, display size, and camera resolution, formatting them as requested. When entities and their structure are too complex to explain, we can use a few-shot prompt. Suppose we have 2 support ticket examples from 2 customers using a travel booking application and their extracted entities. The structure is complex, with parent entities like customer and reservation details, and sub-entities that vary depending on the information found in the corresponding ticket. For instance, entities 1 has phone, but entities 2 does not. Suppose we have this new ticket, ticket 3, from a customer named David and want to extract its entities in the same way as the previous 2 tickets. We formulate a few-shot prompt containing the example tickets, their extracted entities, and the new ticket. The model extracts the entities from ticket 3, following a similar structure to the provided examples and capturing new sub-entities such as the customer ID. The final business applications we will cover are code generation and explanation. Let's explore creating and explaining code snippets with effective prompts. Code generation creates code to solve a problem and is essential in any domain that uses software. Using LLMs for this purpose requires a solid understanding of the generated code for practical use. To generate code, the prompt should include the problem description, target programming language, and desired format such as script, function, or class. For example, asking for a Python function to calculate average sales per quarter, the model generates a function named calculateAverageSales that takes a quarterly sales list, sums the elements, divides by the list length, and returns the average. Sometimes we use input-output examples instead of explicit problem descriptions to generate a program. For example, here we have input lists of quarterly sales of 4 numbers each and corresponding outputs, but we need to understand how outputs are generated based on the lists. We can ask the model to write a Python program for this. The model first identifies that an average function maps each input to its output. Then, it provides the corresponding function and shows how it applies to the examples. Instead of generating code from scratch, we can ask the model to modify existing code. For example, given a Python script that calculates and prints total sales from a quarterly sales list, we can ask the model to transform it into a function that we can call to compute the total sales. The model generates the requested function that computes the total sales and the modified script that calls it on a quarterly sales list. We can include multiple modifications in a single prompt. Using the same script we had, we can ask the model to allow users to input parameters interactively and test if they are positive, returning an error message if they are not. The model makes the necessary changes. The code now takes 4 inputs interactively, displays an error message for negative values, and computes the total sales. Sometimes, pieces of code can become very difficult to interpret, especially if they are lengthy. LLMs can help explain such code. When asking the model to explain a specific code, we should specify the desired explanation length. For example, asking for a one-sentence explanation results in a high-level summary, like stating that the code calculates the average sales per quarter. We can also ask the model to explain the code in detail. In this case, we use a chain of thought prompt asking the model to think step by step. We apply this prompt for the same code we had earlier. The model will take one code chunk at a time and explain its functionality. It explains step by step what happens in each part, starting with the function definition, moving into the computation, and then returning the results. Finally, it summarizes the purpose of the code. Let's explore prompt engineering for chatbot development. Effective prompts help optimize the use of LLMs. But why is prompt engineering vital for chatbot development? Predicting user questions is challenging, even with valuable data on site searches and queries. This is where prompt engineering can guide the chatbot's behavior in answering questions, ensuring reliable and effective responses. How do we achieve this using the OpenAI API? Recall that every message we send has a designated role. Until now, we've only examined user messages due to the emphasis on user prompts. We will focus on system messages to build a chatbot since these guide the model behavior when answering users. The chat completion endpoint is ideal for chatbot development. Via this endpoint, we send messages as lists, each with a specific role. In this example, we send a system message that directs the chatbot to act as an expert data scientist, simplifying complex ideas, followed by a user message seeking an explanation of prompt engineering. In output, we observe how the response uses an analogy of instructing a robot to prepare a sandwich. Previously, we wrapped code into the getResponse function for a single prompt. Now, we will modify it to receive 2 prompts, a system and a user prompt. We will have to pass 2 messages to the function whenever we call it. The first thing to specify in a system's message is the chatbot's purpose. For instance, if we build a financial chatbot, we can give the model this information through the system prompt, and when a user asks a question like, "Who are you?" the model will know how to answer. Specifying the purpose will let the chatbot know what questions to expect. Clear purpose improves domain-accurate assistance, while vague or undefined purposes may lead to irrelevant answers. We should also incorporate clear response guidelines to direct the model's behavior, including the target audience, expected tone, output length, and output structure. We won't need to define everything, but should be specific about what suits our use case. In the example of a financial chatbot, we might direct the model to respond precisely, formally, and objectively. Suppose a user asks for the chatbot's opinion about cryptocurrencies through a user prompt. We see how the chatbot answers precisely, starting with the definition of cryptocurrencies, and then detailing their advantages and disadvantages to remain objective. And finally, it provides a summary. We'll also want to consider using conditional prompts for behavior guidance, guiding the model on how to respond. For example, we might not want the financial chatbot to answer queries not related to finance. To do so, we tell the model in the system prompt to answer financial questions to the best of its knowledge. And for the other questions, the answer should be, "Sorry, I only know about finance." Consequently, if a user asks about the weather, the chatbot will clarify that its only domain is finance. An important aspect to discuss when talking about chatbot development is role-playing prompts. Let's see what these are. Role-playing prompts instruct the chatbot to adopt a specific role, like an actor in a play being given a character to portray. This means adjusting tone, vocabulary, and behavior to fit the role's requirements, providing tailored responses instead of generic ones. This approach ensures effective interactions, especially for domain-specific chatbots. The chatbot learns these roles from its training data. We'll start with an example to understand role-playing prompts, then move to implementation. Imagine we're developing a chatbot for a company offering high-tech products. A customer asks about the technical specifications of a certain product. We've defined 3 roles for the chatbot: customer support agent, product manager, and sales engineer. How would each of these roles answer the user query? The customer support agent provides general guidance, directs customers to the website for more details, and offers assistance. The product manager highlights strategic benefits, focusing on how the product aligns with goals and professional needs. The sales engineer focuses on technical specifics, discussing processor details, features, and security. From this example, we can see how each role can affect the response. And now let's move to implementation. We have to tell the model to act as a specific role, no matter what that role is. For instance, we can ask the model to act as an expert financial analyst and then ask it to offer insights about retirement planning for individuals approaching retirement age. We see how the response gets shaped as if a real expert in financial analysis is providing it, highlighting several considerations to remember when planning their retirement. Role-playing prompts involve assigning specific requirements beyond assigning a role. For instance, although 2 journalists share the same profession, they might differ in traits such as personality and expertise. For example, we can ask the chatbot to embody a seasoned technology journalist specializing in thorough tech industry analysis. Then, ask about the impact of AI on job markets. Here, we can see how the model responds as a journalist with the qualities we described, providing a detailed analysis of the topic in the article. As a final note, we should keep in mind that role-playing does not eliminate the need to specify other requirements like behavior or response guidelines. For instance, in the journalist chatbot scenario, if we wanted to exclusively handle tech-related questions, we modify the prompt to test this condition and let it display an appropriate message if not satisfied. If a user asks about a topic like American literature, the chatbot will clarify its specialization in technology. One key consideration when creating a chatbot is incorporating some external context. Let's explore why that's important and how we can achieve it. We use a pre-trained language model when building a chatbot using the OpenAI API. Such models only recognize specific information they have been trained on. However, we might want our chatbot to know more than that. We should provide it with some context about the missing information to ensure it responds accurately and effectively to user queries. But why does certain information seem to be missing? There are 2 main reasons. First, language models are trained on vast web data. If we ask about events after the model's training or knowledge cutoff, they may struggle or invent answers unless they have access to real-time browsing. For example, a model trained in 2021, when asked about 2023 financial trends, might say, "I apologize, but as of my last update in 2021, I don't have information about financial trends in 2023. Second, the information might not be publicly available, so the model wouldn't know the answer as the information would have been outside the scope of their training. For example, if we ask the chatbot to act as a study buddy and then ask the name of a favorite instructor, it won't know it since this is personal information. We need to provide additional context for the chatbot to answer users' questions. This context can be given as samples of previous conversations or through the system's initial prompt. We can guide the model with sample conversations. For example, we can tell the model via a system message that it's a customer service chatbot. We then provide a user prompt asking about services and an assistant response listing them. The model will use this context to answer questions such as how many services are offered. A disadvantage of this method is that it may require many sample questions and answers. A more effective way of doing this is to provide the context inside the system prompt. Suppose a company named ABC Tech Solutions wants the model to know about their services. The company should define them initially inside a string variable. Then, the system prompt will include these services and the classic parts of the system prompt we've learned about, including the chatbot's purpose and behavior guidelines. When a user asks about the company's services, the model will respond with 3 services from the system prompt: web application development, mobile app development, and custom software solutions. One thing to note is that these methods will work well for relatively small contexts because any LLM will have some limitations in the amount of context it can handle. When a large amount of context is needed, more sophisticated techniques should be applied, which are outside the scope of this course.
Hello and welcome to the course. I'm Francesca, and together we'll learn about best practices for developing real-world AI systems using the OpenAI API. So far, we've explored making requests to the OpenAI API model using the Python OpenAI library, calling the API, and extracting the response to access the output. To connect to the OpenAI API and request the use of a model, we initialize an OpenAI client, create a request to the chat completions endpoint, and specify the messages to send to the model, including the role and content. Finally, we extract the content returned by the model from the API response. In this video, we're going to delve deeper into the foundations of structuring an API call for production environments, a key step towards fully leveraging the capabilities of the OpenAI API. Picture developing an AI application as navigating through traffic. A basic API call is like choosing a route on a map without much consideration for the real-time changes. For efficient and optimized navigation, a well-structured API call is like utilizing a GPS system, specific, responsive, and ensuring a safe journey to your destination. When integrating with more complex production environments, we may need additional features. Our API call should be able to handle errors in a user-friendly way by displaying easy-to-understand error messages and proposing alternatives for when the service is unavailable. It should include moderation and safety features, such as handling of unwanted inputs and safety of ingested data, including minimizing the risk of data leaks. It should also include testing and validation to avoid responses that are out of topic and inconsistent behavior. Finally, it should be structured to easily interface with external applications, functions, and APIs, optimizing response times. But before diving deeper, let's first have a look at how to structure an OpenAI API call to request a more standardized output. In order to better integrate with external applications, it is preferable to output the model response in a format that is easily recognized, such as JSON. This way, other functions in the pipeline can easily access the results. In this example, we're asking to list 5 trees with their scientific names. This can be done by specifying the response format parameter that can be set to formats such as JSON and text. setting it as type JSON object allows us to extract relevant data when communicating with external applications. In addition to the parameter, note that we also specify the format in the prompt. For chat completions, the response is an object from which we can access different elements, including the response message, by accessing the first element of choices, then message, content. In previous courses, we have seen responses as unstructured text, but when using JSON mode, the message content will be structured as asked in the prompt. Now that we've covered the fundamentals of structuring an API call, we have made the first step on the journey to creating a successful AI application on the OpenAI API. In the rest of the course, we'll explore more ways to ensure smooth integration into production, using the API to interact with external functions, as well as follow best practices to build our code. Just like a well-planned route, a well-planned and executed API call sets the stage for a successful AI application. Welcome back! As we integrate the OpenAI API into other projects, encountering errors will be inevitable. Understanding the different error types and their causes is crucial for effective troubleshooting. Error handling isn't just about understanding issues with the code. As AI systems are typically complex, simplifying the user experience becomes particularly important. It eliminates potential barriers to using these systems. For example, in the case presented here, our code uses correct syntax, but we have specified a model that is no longer supported, and so the function won't run. Errors such as this one can be handled in applications in such a way to minimize the impact on the end user. Let's begin by examining a few of the error types in the OpenAI Python library and the respective solutions. Errors that occur due to connection or server issues on either the user's or the services side are, for example, internal server error, API connection error, and API timeout error. In these cases, the best solution is to check our connection, including any firewalls that might be blocking access, then wait and retry after a few minutes, and to get in touch with support if the error persists. Errors can also occur due to limits to the size or frequency of requests, such as rate limit error and conflict error. Here the solution is to ensure that the requests are paced within the limits of the API, such as reducing the amount of text in the request sent or staggering requests if they are frequent. Some errors will more likely require fixes that we can implement within the code. For instance, in this example, we're passing an invalid key for authentication. An authentication error occurs when our API key or token is invalid, expired, or revoked. To resolve this, we need to ensure that our API key or token is correct and active, and that its access has not been revoked. If the key has expired, we may need to generate a new one from the OpenAI account dashboard. A bad request error indicates that our request was malformed or missing some required parameters, such as in this example, where we're passing an invalid role to the message dictionary. To fix this error, we should review the error message, check the documentation for the specific API method being called, and ensure that we're sending a valid and complete parameters as input to our request. One example where this error may occur could be if any of the required keys were missing from the message dictionary, such as in this example where the message role is neither system, assistant, user, or function. To manage unanticipated exceptions, we use try and except blocks to allow our program to continue to run. Let's take a look at an example. By encapsulating our function call within a try block, we attempt to execute it. First, there is an attempt to execute the code within the try block. If an error occurs during this execution, the code looks for an except block that matches the type of error that occurred. If we encounter errors specific to the use of the OpenAI library, such as authentication or rate limit errors, we can use the except block to catch these particular exceptions and handle them accordingly. If a generic error occurs, the code moves to the last except block, allowing the program to continue execution without disruption. Welcome back! We're now going to dive deeper into the rate limits error. Handling this error will help us maximize the requests to the API while minimizing delays and avoiding failed responses. Let's get started. Rate limits in an API are like traffic regulations on a busy highway. Just as traffic lights, speed limits, and lane restrictions are in place to ensure smooth and safe traffic flow, rate limits regulate the flow of data between users and the API. By avoiding single users from making excessive requests, rate limits can prevent malicious attacks as well as ensuring a balanced distribution between users within an organization. A rate limit error can be due to either the number of requests in a given time span being too high, meaning there are too many requests being sent, or the number of tokens in the requests exceeding certain limits, meaning too much text has been included in the request. Some solutions to avoid these limits include performing a short pause between requests, setting the function to retry in case limits are hit. If the frequency of the request is hitting the rate limit, multiple requests can be sent in batches at more staggered time intervals. This is referred to as batching. If the tokens limit is hit, the number of tokens can be quantified and reduced accordingly. When sending requests that might go above the rate limit due to their high frequency, we can set our function to automatically retry in case the limit is hit. One way to approach this is by adding a retry decorator using Python's Tenacity library. A decorator is a way to slightly modify the function without changing its inner code, and the retry decorator is used to control the extent to which the function should be run again when failing. The wait parameter can be configured through the wait random exponential function. Using the exponential backoff mode is a way to automatically retry requests with gradually increasing delays from a minimum in this case of 1 second to a maximum value in this case of 60 seconds. The stop parameter can be specified using the stop after attempt function and specifying the maximum number of tries. To use the decorator, we'll have to wrap our response request as a function, such as in this example where we have a getResponse function returning the message. If the rate limit is hit due to the timing of the requests and not the number of tokens, one way to avoid it is to send the requests in batches. In this example, we're asking the API to return the capital city for each of the countries given, through a list of dictionaries passed through the API. Notice that in this case, we have specified precise instructions as the system message, in order to get a full answer with all 3 responses. This is a much more efficient approach than looping through the chat completions endpoint, passing 1 country per iteration. Another way to avoid rate limit errors, if the time frequency of requests is not an issue, is to reduce tokens. Tokens can be thought of as chunks of words that constitute units of a word. One way to measure tokens in Python is to use the tick-token library. This way, we can first create the encoding using the encoding for model function and selecting the model we're using, and then count the tokens in the prompt, such as in this sentence we have in this example, using encode and obtaining the total number using the len function. Each OpenAI model has different limits to the number of tokens that it can handle in input, and this also constitutes a way to check that the prompt is below those limits. Welcome back! In this video, we will introduce OpenAI's function calling feature, exploring some concepts before moving to its applications in the next video. OpenAI endpoints support tools that can be defined to have the models return more specific information or return more precise outputs by defining a certain structure. Tools are options given to the endpoints to enhance the capabilities of the API call. Let's consider an example where we wanted to use the OpenAI API to control a smart home device, such as a smart light bulb. We could create a function that takes a natural language command, sends it to the OpenAI API for processing, and then interprets the response to control the hardware accordingly. The response should be interpreted consistently across different users, so we'd have to make a change to the original API call. This is where tools come in. By defining certain rules, we set the model output to follow a precise structure. To specify this type of behavior, we'd have to define our tool as a function that outputs the expected response, hence the name function calling. So far, the way we've generated structured outputs has been to have the API generate JSON outputs by specifying the response type and passing a system message, such as in this example where we're asking to output scientific names of trees in JSON format. Up to this point, however, the reliability of our outputs has remained limited, as the JSON keys created when calling the endpoint this way are purely based on the model's interpretation, which can sometimes be inconsistent, such as in this example where different dictionaries containing names of trees have been generated using the same endpoint and prompt. Function calling addresses this issue by enabling OpenAI models to take user-defined functions as input, resulting in consistent responses without the need for complex text processing techniques. By ensuring a reliable structure of our API response, we can integrate our AI application with external systems and be more certain of its reliability. For instance, we can extract instructions from our natural language input and pass them to a smart home system. We can call multiple functions to provide complex responses, formulated by means of different functions. For example, in an e-commerce customer service chatbot, where the prompt given as input could trigger different functions, such as a function that retrieves the product catalog, one that reads from the website's FAQs, or another that provides a response. Finally, we can use function calling to define functions that enhance the responses by calling external APIs, such as for a weather chatbot calling an API to return current temperatures at specific locations. Now that we are familiar with function calling, we'll take a look at how it can be utilized in practice. In this video, we'll dive into using function calling to extract structured data from unstructured text. Let's say we wanted to extract specific parameters from this job description for a data scientist role. Instead of passing a prompt asking to return a JSON and a response type as in previous cases, we add a new function definition to request the specified output. This is done through the tools parameter that we add to the chat completions endpoint. When defining a function to be passed to the tools argument, the format is a list of dictionaries. Let's take a look at how to build one. First, we specify the type of tool as function. The function type is used when we want to call our own user-defined function. We then move to specifying information about the function itself. Under the function key, we specify a name for the function, a description of what the function should do, and its parameters. In this case, we provide a name for our function related to extracting job information, a short description stating that the function gets information from text, and parameters. Let's now take a look at setting the parameters within the function. In the parameters dictionary, each key is the key that will be included in the resulting JSON schema. Each value is a dictionary containing the type of data it will hold and a description to help the model extract it. In this example, the keys are job and location. They are both strings, and we provided short descriptions to state that they refer to the job title and office location. Finally, let's take a look at the response from our API request that uses function calling. One thing that changes from previous calls is that when using function calling, the response will be nested in tool calls function arguments. Notice that tool calls is a list, as there is an option to call multiple functions, and in that case, each item in tool calls will contain the response from each function. In the example we have, the job and location extracted from the job advert are the outputs. Now that we know how to use function calling to extract structured data, we're ready to add a new functionality to our API call, passing multiple functions to be used in the response. The ability of the model to handle multiple functions is called parallel function calling. Parallel function calling enables an improved communication with the model, enhancing its ability to process and generate responses. Let's go back to the previous example where we wanted to extract job information from job descriptions and assume we'd like to concatenate an additional function to the first one. In the function definition, we'll keep the previous function to extract the job data. But this time, let's say we'd also like to know the time zone that corresponds to the location in the job advert to check the feasibility of working remotely. We set up this function in the same way as for the first one and add it to the list using append. And finally, as we did before, we trigger function calling by passing our function definition to tools. In the case of calling multiple functions, we'll have to use indexing to select the different responses from the tool calls list, as shown. We might end up with a long list of functions in our tools, and in that case, the default behavior of the model is to choose which one to use based on the message and function definitions. This is the equivalent of setting tool choice as auto. If we want the model to pick a specific function from our list, we'll have to modify tool choice from auto to a dictionary containing the name of the function we'd like the model to use. When setting specific functions, the model can make assumptions about values to assign, even if they are not present in the message. To avoid this behavior, a good strategy is to use the system message to communicate this to the model. Before specifying the user message, for example, we could write a couple of system messages asking not to make any assumptions and to ask for clarification if needed, such as the ones shown. One thing to account for in this case is that the model might return an empty dictionary if it cannot find anything suitable to respond to the prompt. Let's test the behavior of the model by asking for a piece of information that is not in the job description provided, the starting salary for the role. In this video, we'll explore how function calling can be used to call external APIs to retrieve additional information. APIs are widely used in software engineering and facilitate communication between different software systems. There is a variety of them available and open without the need for a subscription. For example, the Art Institute of Chicago has one available for free that provides developers with the museum's public data. In Python, we can use the request library to call the API by providing its URL and query parameters. Our query parameters are the values required as input to the API call for the external API. We then specify the type of request and pass URL and parameters to the request function to get a response. Using the Art Institute API with the OpenAI API, we could provide suggestions on artwork to see at the museum based on a user input. The first thing to do is to package the API call as a function that we're going to call getArtwork, that returns the recommended artwork based on an input keyword. We then move to setting up the chat completions request. As we've seen, it is important to give context to the model, and in this case, we want to make sure it uses the user message to generate one keyword that will then be used as input for calling the external API. So we provide a specific system message asking to interpret the prompt and based on it, extract one keyword for recommending artwork related to their preference. For this example, we also provide a user message that could be coming from a tourist wanting to visit the museum. In the endpoint call, we specify the getArtwork function as part of the tools in the endpoint request. As for the functions previously seen, we set the parameters including type and properties and add the expected result type. In this case, the function will extract a keyword from the user input that will then be passed as an argument to the function calling external API. The parameter's properties in this case should be the artwork keyword with its type and description. We need to include some handling of the response before calling the APIs. First, we import the JSON library that we'll use to convert the response to a dictionary. We then want to check that there was a call using the function in tools. To do this, we check that finish reason in response choices equals tool calls. If so, we extract the function called using function in message tool calls. If not, we print a message to the user stating that the request could not be understood. The next step is to extract which function was called, using name from function call. If the function called is getArtwork, we extract the keyword from the function call arguments. Once the keyword is extracted, we can proceed to call the external API using the getArtwork function. Finally, if the external API returns a response, we extract our recommendations. In this case, we use a dictionary comprehension to extract the response due to the format of the output in the external API. But this varies based on the external API's output format. And finally, we have a response that we can use to pass back to the user, a list of artworks from the museum that resonates with the user who likes the seaside. Depending on how the external API is set up, there might be some post-processing to do on the output that can always be done using standard Python code. Welcome back! We have now come across various techniques to develop advanced systems using the OpenAI API. To ensure that these systems are robust and reliable, we should follow best practices in moderating, validating, and securing content. Moderation in the context of the OpenAI API refers to the process of analyzing input to determine if it contains any content that violates predefined policies or guidelines. It is a critical aspect of managing user-generated content. OpenAI provides a moderations endpoint as part of its API to help developers automatically flag and filter out such content that violates community guidelines. The moderation endpoint uses OpenAI's models to evaluate text and assign a probability for each category of content violation. These categories have been selected by OpenAI and are hate, harassment, self-harm, sexually explicit content, and violent content. In the following code examples, we'll test the OpenAI API in moderating some text excerpts. Here we have extracted part of the instructions of the game Exploding Kittens and are passing it to the moderations endpoint as an input using client moderations create. Let's have a look at how the moderations endpoint classifies it for the violence category. Without much context, this part of the game's instructions has been classified as violent, and so the output to the violence category is true. Let's now test the same instructions, but this time giving the full text that includes more context and mentions the fact that it is a game. In this case, the model recognizes the context and this time doesn't classify the content as violent, so the output to the category violence is false. As we integrate AI more deeply into our systems, the complexity increases and we might end up with larger volume of text, making it more challenging to identify malicious content. This gap in moderation capabilities opens the door to prompt injection attacks, where malicious actors manipulate AI models to produce undesirable outcomes. Several strategies can be used to mitigate the risks associated with prompt injections. First, limiting the amount of text a user can input is a straightforward yet effective measure. Similarly, constraining the number of output tokens generated can significantly decrease the chances of misuse. Finally, narrowing the range of acceptable topics by drawing inputs or outputs from trusted sources can also ensure a higher degree of reliability in the system's responses. For instance, configuring the system to return outputs from a validated set of materials can be much safer than letting the model generate completely novel content. In certain applications, we might want to avoid certain topics as they are outside the scope, while at the same time they don't belong to any of the moderated categories in the API. In this case, we present the model with the same instructions for the game Exploding Kittens, but this time we want to only allow prompts about the game of chess. We need a way to instruct the model to avoid these topics, and so we provide a system message to specify this. These instructions given to steer the model away from going off topic are called guardrails. These are not implemented through the Moderations API, but by passing a system message to the chat completions endpoint. Let's go back to the code example, where the messages on the previous slides are now passed to the chat completions endpoint. As we want to only allow topics related to the game of chess, when we pass the instructions for Exploding Kittens, the model returns a response saying the topic is not allowed. In this video, we'll continue our journey to ensure that the AI systems we're building meet expected standards and provide good quality content to users. With validation, we are testing the model's performance to uncover areas where the model might be prone to making mistakes. Validation is aimed at uncovering a variety of cases that mimic its use in the real world, such as misinterpreting context, amplifying biases in its outputs if the training data is biased, outputting outdated information, being manipulated to generate harmful or unethical content, or inadvertently revealing sensitive information. A valid method for testing AI systems before they are released is adversarial testing. Adversarial testing involves in providing the model with prompts that are specifically designed to identify its areas of weakness so that they can be addressed before release. It is a technique used with other AI systems beyond large language models, where even a small change in input can produce an unwanted or wrong output. Let's have a look at an example. Here we have some movie reviews and are asking the model to extract the sentiment from each, positive, negative, or neutral. Here is an example of a movie review that seems to start on a positive tone, but turns negative towards the end, which might make it more difficult for the model. The model recognizes this nuance and gives the correct answer, which is that the review is negative. This is another difficult example that we've selected to test the model, another film review. In this case, it fails to recognize the sarcasm, categorizing the review as neutral. To evaluate models in a more structured way, researchers are developing libraries and datasets of standardized use cases that measure the model's performances in a variety of domains. The datasets represent a variety of use cases and include metrics that can be used for the evaluation. These have been introduced to address issues found in previous evaluations where there was a disconnect between the benchmarks and the capabilities of the models in the real world. They provide assessments across a range of domains, including STEM, humanities, and social sciences, with difficulties ranging from elementary to professional, and this has been shown to be a more effective representation of models' behavior in the real world. In this last video, we will explore the best practices for maintaining safety while using the OpenAI API. In addition to the techniques we've seen so far, there are multiple ways to ensure safety when developing AI systems. AI safety encompasses multiple disciplines and needs to ensure that the content generated is safe, including following ethics and fairness guidelines. As the content generated is not strictly set by the developers of the product, safety also needs to ensure that it is aligned with the scope of the product. Finally, it also includes traditional safety measures for software systems, including keeping data safe and securing the whole system against attacks. We have already explored some steps to keep the responses within ethical guidelines and to keep the content relevant. One of these is using Moderation API to reduce the occurrence of unsafe content. We've also seen how adversarial testing is used to ensure applications are robust against inputs designed to break the underlying models. We've seen how limiting the number of output and input tokens can prevent prompt injection and misuse. Finally, crafting prompts to guide the AI's output in terms of topic and tone and adding context can help steer outputs in the right direction. Let's have a look at additional measures we can take. When possible, content safety can be enhanced by incorporating human oversight, particularly in specialized domains. This could involve having outputs sampled and checked by a professional with domain expertise, with the development team integrating their feedback back into the model. Requiring users to register and log in to access our service can further reduce risks as it constitutes an additional check. Providing users with a clear method for reporting issues with the application is a way to have additional oversight. For the security of our data and our system, it is also important to keep our API key, that we have used throughout the course, in a safe and private environment. Finally, it is important to recognize that all language models have limitations, and to communicate this to our user base to manage expectations. As a way to prevent malicious actors from misusing our AI systems, OpenAI suggests including unique user IDs in requests. This ensures that the API call can be easily identified in case of guidelines violations. It can be done by hashing usernames for registered users and, for non-registered users, by passing unique session IDs. In Python, we can use the UUID library and generate universal unique identifiers using UUID4. We can then cast the ID as a string and pass it to the chat completions endpoint, such as in this example. We have seen throughout the course how the OpenAI API is accessed by passing a key. The key is used to keep the communication between our system and the API safe, and it is important to keep it secure. Here are some best practices to ensure this. Keeping API keys server-side to avoid exposure in client-side environments like browsers or mobile apps. Never committing API keys to source code repositories. Instead, using environment variables to save the key, even in private repositories. Utilizing key management services for secure API key storage and access control. Regularly monitoring account usage and rotating API keys.
Hi, welcome to the course. I'm Emmanuel, and I will be your guide as we learn about embeddings and the powerful applications they unlock. Let's dive right in. Embeddings are a fundamental concept in natural language processing, or NLP, where text, which can be words, phrases, or entire documents, are represented in numerical form. More specifically, embeddings model map text onto a multi-dimensional space, or vector space, and the numbers outputted by the model represent the location of the text in that space. More similar pieces of text or words, like teacher and student, are mapped closer together in the space, and dissimilar words are mapped further away. This ability to map similar and dissimilar words means that embeddings models can be used to capture the semantic meaning of text. By semantic meaning, we mean that the full context and intent of the word is captured. For example, which way is it to the supermarket? And could I have directions to the shop? Are semantically very similar, but only share two words in common. A model using embeddings would recognize the semantic similarity between the two variations and return similar information. Let's take a look at some of the most powerful use cases being enabled by embedding models. Embeddings enable the creation of semantic search engines. Traditional search engines use keyword pattern recognition to return relevant results. For example, searching comfortable running shoes on a traditional search engine may return results containing the keywords comfortable, running, and shoes, but may miss the true intent behind the searcher's query. It will also miss variations on the word provided, like soft instead of comfortable and sneakers instead of shoes. Semantic search engines use embeddings to better understand the intent and context behind search queries to return more relevant results. The search query would be passed to an embedding model to generate the numbers that map it onto the vector space, and the embedded results closest to it would be returned. Embeddings also enable more sophisticated recommendation systems. For example, a job posting website could use embedding models to recommend jobs for its users based on the description of jobs they have already viewed. Using a semantic recommendation system means that even if job titles vary, the system will recommend jobs with descriptions that are most semantically similar to the jobs that have been previously viewed. The final use case we'll discuss is classification, which works very similarly to recommendation. This can be used to classify sentiment, cluster observations, or perform categorization, all based on the semantic similarity between texts. We could use embeddings to classify news headlines by embedding the headline and assigning the label closest to it. OpenAI provides access to their embedding models via the Embeddings endpoint, and requests to it take a very similar form to other OpenAI endpoints. We'll use the OpenAI library to create requests to the OpenAI API, which also requires us to have an OpenAI API key. To begin our request, we first need to instantiate the OpenAI client and pass it our API key. To create the request, we call the create method on client.embeddings. An OpenAI embeddings model can be specified with the model argument, and the text to embed is passed to the input argument. We are specifying the input here as a text string, but the argument also accepts a list of strings. Finally, we'll call the model dump method on the response to convert it into a dictionary, which is easier to work with and print the result. The response from the API is extremely long, as the embedding models outputs 1,536 numbers to represent the input string. Because we converted the response into a dictionary, we can dig into it using lists and dictionary subsetting. Here we can print the full list of 1,536 numbers representing our text. Welcome back! In this video, we'll discuss embedding multiple inputs and how to store, handle, and explore these embeddings. Let's dive in. We'll be working with a dataset of news articles stored in a list of dictionaries. Each article has a headline stored under the headline key and a topic stored under the topic key. We'll embed each headline's text and add them back into the headlines dictionary stored under the embedding key. To start, we'll extract each article's headline using a list comprehension, accessing the headline key from each dictionary. To compute the embeddings, we can pass this entire list as an input to the create method. Batching the embeddings in this way is much more efficient than making API calls for each input. The response output only differs from the single input case in one way. Where before the list under the data key contained a single dictionary for the embeddings, in the multiple input case, there is one dictionary for each input. To extract these embeddings from the response and store them in the articles list of dictionaries, we loop over the indexes and articles using enumerate. For each article, we assign the embedding at the same index in the response to the article's embedding key. Let's print the first two articles. Voila! We've successfully created embeddings for multiple inputs. Let's investigate these numbers more closely. For the first article in the list, the embeddings model returned 1,536 numbers representing the semantic meaning of its headline, or in other words, its position or vector in the vector space. Let's take a look at another longer headline. We get 1536 numbers again. This is a key property of OpenAI's embedding models. They always return 1536 numbers, no matter the input. Let's visualize our embeddings to better understand the model's results. We'll first need to reduce the number of dimensions from 1536 to something more manageable, like 2. There are a lot of techniques for performing dimensionality reduction, but we'll be using t-SNE, or T-Distributed Stochastic Neighbor Embedding. Although we won't be going into the mechanics of how t-SNE works, you can check out the datacamp link to learn more. We'll implement t-SNE using scikit-learn, a popular Python package for machine learning tasks. First, we import t-SNE from sklearn.manifold and numpy as MP. Next, we'll extract the embeddings from our articles list of dictionaries using list comprehension. To implement t-SNE, we create a t-SNE instance and assign it to the t-SNE variable. We've specified 2 arguments: endcomponents, the number of dimensions we want to reduce to, 2, and perplexity, which is used by the algorithm in the transformation. The default value of 30 is normally fine, but for smaller datasets, it must be reduced to a number less than the number of data points. We have 10 articles in our dataset, so we've reduced perplexity to 5. Finally, to perform the t-SNE transformation, we call the fitTransform method on the t-SNE object, passing it the embeddings as a numpy array. This will return the transformed embeddings in a numpy array with n component dimensions, which we can now visualize. Although t-SNE is useful for exploring and visualizing higher dimensions, it will result in the loss of some information in the transformation, so it should be used with caution. To visualize these transformed embeddings, we call plt.scatter from matplotlib on the first and second columns of the embeddings to the array. We'll also include some code to extract the article topics, annotate the plot with them, and display the plot. Here is the plot. Notice that headlines with the same topic were clustered more closely together. In other words, the model captured the semantic meaning of the headlines and mapped them based on it. In the next video, we'll discuss how to compute the similarity between embeddings to enable applications like semantic search. Let's round out the chapter by looking at how we can compute the similarity between 2 pieces of text using embeddings. Recall that embedding models map semantically similar text more closely together in the vector space. This means that we can measure how semantically similar 2 pieces of text are by computing the distance between the vectors in the vector space. Being able to measure similarity is what will enable the embeddings applications we've discussed previously: semantic search, recommendations, and classification. There are many different metrics for computing similarity in higher dimensions, but we'll be using cosine distance. The cosine distance uses linear algebra, a branch of mathematics, to evaluate the similarity between 2 vectors. Let's start with a small example of 2 points in 2 dimensions. To compute the cosine distance between the 2 points, we can import distance from scipy.spatial and call distance.cosine, passing the coordinates of the 2 points. The result is 1. This is difficult to interpret on its own, but the distance can range from 0 to 2, where smaller numbers indicate greater similarity. Let's try this out with text embeddings. Let's return to an earlier dataset of news article information, including headlines and topics, which are stored in a list of dictionaries. The article headlines have already been embedded using OpenAI's embedding model and stored under each article's embedding key. We'll use these embeddings to compare how similar our headlines are to another piece of text and find the most similar one. To create embeddings in a more repeatable way, we'll define a custom function to send a request to the API and extract and return embeddings from the response. This function can be called on a single string or on a list of strings and always returns a list of lists. To just return a single list of embeddings for the single string case, make sure to zero index the function's result. First, we'll import distance from scipy.spatial for the cosine distance calculations, and numpy to access its argmin function, which returns the index of the smallest value in a list. Let's start with a piece of text to compare to our embedded headlines. Computer. We start by embedding this text using our createEmbeddings custom function, remembering to zero index the result. To find the most similar headline to this text, we'll loop over each article, calculating the cosine distance between each embedded headline and the embedded query. We start by creating an empty list to store our distances and loop over each article in our articles list of dictionaries. Next, we calculate the cosine distance between the text and headline by calling distance.cosine, passing it the embedded text and headline. Finally, we append this distance to the distances list. The most similar headline will have the smallest cosine distance, so we can use numpy's argmin function to return the index of the smallest value in the distances list. Then, use it to subset the article at this index and return its headline. There we have it. The most similar headline to the text computer was one about a new tech product. Pretty neat. In this chapter, we'll begin to apply what you've already learned to implement the most popular embedding applications: semantic search, recommendation systems, and classification tasks. Let's start with semantic search. Recall that semantic search engines use embeddings to return the most semantically similar result to a search query. For example, a news website could enable semantic search by embedding news article information like the headline and topic. A user searching computer could then be returned a selection of computer-related headlines. There are 3 steps to semantic search: embed the search query and text to compare against, compute the cosine distances between the embedded search query and other embedded text, and finally, extract the text with the smallest cosine distance. Let's implement this semantic article search using the OpenAI API and Python. Here's the headlines data we'll be working with. We'll embed not only the headline text, but also the topic and keywords. To do this, we'll combine the information from each article into a single string that reflects the information stored in the dictionary, and the keywords are delimited with a comma and space. To combine these features for each article, we'll define a function called createArticleText. This function uses an f string or formatted string to return the desired string structure. F-strings allow us to insert variables into strings without having to convert them into strings and concatenate them. F-strings are created by specifying an f before the quotes, and note that we've defined a multi-line string using triple quotes. To insert an object, we use curly brackets and specify the variable or other Python code to insert. For the article headline and topic, these values are extracted using their keys and inserted into the string at the desired locations. The keywords are a little trickier because they were stored as a list rather than a string. To convert the keywords list into a string, we use the joinList method, which joins the content of the list together into a single string. The method is called on the string we want to delimit each keyword with, in this case, a comma and space. Calling the function on the final headline shows the text in the desired formatted string. To apply the function and combine the features for each article, we use a list comprehension, calling our function on each article in articles. Finally, to embed these strings, we call the createEmbeddings function on the result. Recall that this creates a list of embeddings for each input using the OpenAI API. Now that we have our embeddings, it's time to compute cosine distances. We'll define a function called findNclosest that takes a query vector, the embedded search query, and embeddings to compare against, our embedded articles, and return the n most similar results based on their cosine distances. For each embedding, we calculate the cosine distance to the query vector and store it in a dictionary along with the embeddings index, which we append to a list called distances. To sort the distances list by the distance key in each dictionary, we use the sorted function and its key argument. The key argument takes a function to evaluate each dictionary in distances and sort by. In this case, it's a lambda function that accesses the distance key from each dictionary. Finally, the function returns the closest n results. Time to bring all the semantic search pieces together. We'll query our embeddings using the text AI. First, we embed the search query using our createEmbeddings function and extract its embeddings by zero indexing. Next, we use the findNclosest function to find the 3 closest hits based on our article embeddings. Finally, to extract the most similar headlines, we loop through each hit using the hits index to subset the corresponding headline and print. As we'd expect, the top results specifically mention AI, and the others are on similar topics. Welcome back. In this video, we'll discuss another common application of embeddings, recommendation systems. Recommendation systems work almost exactly the same as semantic search engines. We have a group of items that we potentially want to recommend, and at least one data point that we want to recommend based on. We embed the potential recommendations and the data point we have, calculate the cosine distances, and recommend the item or items that are closest in the vector space. This similarity in approach means that a lot of the code is exactly the same. Let's take a look. We are returning to the news article dataset to design a recommendation system that recommends the 3 most similar articles to the one currently being read. This recommendation will be based on the article's headline, topic, and keywords stored in a dictionary called current article. This particular article is about the impact of computer hardware on AI advancement. To prepare both of these objects for embedding, we'll first need to combine the features into a single string for each article. We'll be reusing the createArticleText function you may remember from earlier, which extracts the headline, topic, and keywords and uses an f string to combine them into a single string. To combine the features, we call the function on each article in articles using a list comprehension and do the same for the current article. By printing, you can see that the function correctly formatted the current article's information. Next, we embed both sets of article strings using the createEmbeddings function from earlier, which allows us to create requests to the OpenAI embedding model in a more repeatable way. Finally, to compute the cosine distances and extract the nearest distances, we'll use our findNclosest function, which computes the cosine distances, sorts them, and returns the n smallest and their index. We'll call this function on both sets of embedded articles and then loop through the results, returning the headline of each article in the 3 most similar articles. There we have it. This is a good start, But a more sophisticated system would use not only the current article to base the recommendations on, but also the other articles in the user's history. Let's consider that a user has visited 2 articles stored in user history. How can we provide recommendations based on multiple data points? This is the situation we have, where the user has seen 2 articles embedded in blue, and we want to recommend the most similar articles. Articles they haven't seen yet are shown in red. To find the most similar vector to 2 vectors, we'll combine the 2 vectors into one by taking the mean. Then, we'll compute cosine distances as we did before and recommend the closest vector. If the nearest point has already been viewed, we'll make sure to return the nearest unseen article. The first 2 steps to embed the user history are the same as before, combining the features for each article and embedding the resulting strings. The only difference is that we take the mean to aggregate the 2 vectors into one that we can compare with the other articles. For the articles to recommend, we filter the list so it only contains articles not in the user history. Then, as before, we combine the features and embed the text. Finally, we compute the cosine distances using the same find_n_closest function, only this time passing it the mean of the embedded user history. Then, we subset the filtered article list to find the most similar articles. Here they are. Notice that the article headlined "Tech Giant Buys 49% Stake in AI Startup" wasn't recommended, as the user had already seen it. The final common embedding use case we'll discuss are classification tasks. Classification tasks can take different form, but generally they involve assigning labels to items. Common tasks include categorization, such as categorizing headlines into different topics, and sentiment analysis, such as classifying reviews as positive or negative. Embeddings can be used for both of these cases, utilizing the model's ability to capture semantic meaning. We'll be using a type of classification called zero-shot classification, which means that the classifications won't be based on labeled examples. Let's look at how that works with an example on classifying news articles by topic. First, we begin by embedding a description of each class label. Here, we'll use 4 classes: tech, science, sport, and business. We'll be embedding these labels and using them as reference points to base the classification on. Next, we embed the article to classify and calculate cosine distances to each embedded label. Finally, we assign the article the label with the smallest cosine distance. Let's do this in Python. Here are the topic classes we'll be categorizing with. In this example, we'll categorize using the label itself. So the first step is to extract the labels as a single list and use these as the class descriptions. Then embed each topic label using the createEmbeddings custom function that makes a call to the OpenAI embedding model. Here's the article we want to classify. The first step here is to combine the headline and keyword information into a single string that we can embed. We do this by defining a custom function that uses an F string to concatenate the headline and keywords inside a nicely formatted string. Finally, we can embed the text by calling createEmbeddings again, remembering to zero index the list returned so we have a single list of numbers. Now that we have the embeddings, it's time for the cosine distances calculations. This is a modified version of the find_n_closest custom function from earlier in the course, where instead of returning n results, we only want one, the nearest label. This means that instead of sorting by distance, we can find the minimum using the min function. Calling this function will return the distance and index of this label. Finally, we can use this index to subset the topics dictionary and extract the label. Printing the result, returns the business label. Wait, that doesn't seem right. If we take another look at the article we're classifying, we can see that the headline indicates that the focus of the article is on tech. It's likely that the model captured the business keyword, which resulted in the mislabeling. The limitation in our approach that led to this was that the class descriptions lacked detail. The word business or tech doesn't contain much meaning on its own for the model to capture, so a better approach will be to use more detailed class descriptions. Let's try this again, but instead of using the labels as the descriptions, we use short descriptions to represent each class. The steps here are almost identical. We extract the descriptions in a single list, this time using the description key, and embed them. The rest of the code is the same. This time, when we print the result, we can see that the model classified correctly. Welcome back! In this chapter, you'll learn how to enable use cases with larger datasets by efficiently storing and querying vectors using a vector database. So far, we've created embeddings using the OpenAI API and stored them in memory. Because each embedding contains 1,536 float values, this results in around 13 kilobytes of data for each embedding, which becomes impractical to load for hundreds, thousands, or millions of embeddings. We also recalculated these embeddings with every query rather than storing them for later use. To compare similarity, we computed cosine distances for every embedded document and sorted the results, which are both slow processes that scale linearly. To enable embeddings applications with larger datasets in production, we'll need a better solution: vector databases. Here is a typical embedding application. The documents to query are embedded and stored in the vector database. A query is sent from the application interface, embedded, and used to query the embeddings in the database. This query can be a semantic search query or data to base recommendations on. Finally, these results are returned to the users via the application interface. Because the embedded documents are stored in the vector database, they don't have to be created with each query or stored in memory. Additionally, due to the architecture of the database, the similarity calculation is computed much more efficiently. The majority of vector databases are what's called NoSQL databases, which contrast conventional SQL or relational databases. SQL databases store data in tables with rows and columns. NoSQL databases don't use tables and can be structured in several different ways to enable faster querying. 3 examples of NoSQL architectures are shown, including key value, document, and graph databases. Vector databases aren't only used for storing the embeddings. The source texts are also commonly stored. For vector databases that don't support this, source text must be stored in a separate database and referenced with an ID. Metadata is also stored in the database, including IDs, external references, and additional data that could be useful for filtering the query results. It could be tempting to store the source texts in the metadata, but this should be avoided. Metadata must be small to be practically useful, so adding a large amount of text data will greatly degrade performance. So what are the options when it comes to vector databases? Fortunately, there are plenty of options out there to suit almost every use case. Here are some of the most popular. When deciding which database solution to go with, there are several factors to consider. Vector databases can be managed, which is a turnkey solution that will take care of itself while you concentrate on application features. It does come at a price, but can be a sensible investment. Alternatively, you can self-manage and deploy your own server and database, either in the cloud or on-premise. This is usually cheaper, but requires time and expertise. Open source solutions provide greater flexibility in usage and can be more cost-effective if budgets are tight. In contrast, commercial solutions offer better support, more reliable performance, advanced features, and better regulatory compliance. We should also ask ourselves if our data lends itself to a particular database type. As discussed, there are several NoSQL architectures utilized by different database providers. Finally, does the use case depend on specific functionality, like embedding and storing both text and images for a multimodal application? In this course, we'll be using Chroma, as it's open source and quick to set up. At the end of this course, we'll provide resources for learning more about other solutions. Time to start getting hands-on with ChromaDB. Chroma comes in two flavors: a local mode where everything happens inside Python, and a client-server mode where a ChromaDB server is running in a separate process. Client-server mode requires running a separate process for the Chroma server and is better suited for production systems. We'll only be looking at local mode, which is the simplest way to run Chroma and is well suited for development and prototyping. In order to connect and query the database, we first need to create a client. We import ChromaDB and create a persistent client by calling persistent client. Persistent clients save the database files to disk at the path specified. To add embeddings to the database, we must first create a collection. Collections are analogous to tables, where we can create as many as we want to store our data. To create the collection, we use the createCollection method. When creating a collection, we need to pass the name of our collection, which is used as a reference, and the function for creating the embeddings. Here, we specify the OpenAI embedding function and API key. In Chroma, and in many other vector databases, a default embedding function is used automatically if one isn't specified. The listCollections method lists all of the collections in the database, so we can verify that our collection was created successfully. We are now ready to add embeddings into the collection. We can do so with the collection.add method. In this example, we are adding a single document. Chroma will not automatically generate IDs for these documents, so they must be specified. Since the collection is already aware of the embedding function, it will embed the source text automatically using the function specified. Most of the time, we'll insert multiple documents at once, which we can do by passing multiple IDs and documents. After inserting documents, we can inspect the collection with two methods. Collection.count will return the total number of documents in the collection, and collection.peek will return the first 10 items in the collection. As we can see, the embeddings were created automatically when we inserted the text. We can also retrieve particular items by their ID using the get method. In the following exercises, we'll insert a dataset of Netflix titles into the Chroma database. For each title, we'll embed a source text including the title, description, and categories. While this is not a massive dataset, we must not forget that each of these texts is going to be sent to the OpenAI embedding endpoint and therefore cost money. Before inserting a sizable dataset into a collection, it's important to get an idea of the cost. OpenAI provides the cost per 1,000 tokens on their model pricing page, which means we can find the total cost by multiplying this value by the number of tokens in the text we'll embed and dividing by 1,000. We can count these tokens with OpenAI's tick-token library. Tick-token can convert any text into tokens. First, we use the encoding for model function to get a token encoder for the embedding model we're using. To calculate the total number of tokens, we use the following Pythonic code. This reads, for each text in documents, encode it using the encoder and take the length to obtain the number of tokens in the text. Finally, sum the results. This code is much more concise and efficient than looping through the documents. It just takes a little time to get used to if you're used to looping. Finally, we calculate the price by multiplying total tokens by cost per 1K tokens over 1000 and print the result. We'll work with a smaller subset in the exercises of the first 1000 titles. We meet again. Let's continue our journey to learn about querying and updating our collection. Similar to what we did manually in the previous chapter, we'll build a semantic search application, but this time using a vector database. The approach is exactly the same. We have a query string, and we want to find similar titles in our collection. Previously, we had to embed the query string to get a query vector, which was used to find similar embeddings in the dataset. With Chroma, we'll let the collection do the embedding, so we can pass our query string directly, and Chroma will take care of creating the embedding and performing the search. First, we need to retrieve our collection, which we can do with client.getCollection, specifying the name of the collection to retrieve. Recall that when we created the collection, we specified the embedding function to use, and it's also really important to specify the same function when retrieving the collection. This way, Chroma will use the same embedding function to create the query vector. To query the collection, we call collection.query, passing our query string to query text. Note that this parameter is plural, so even if we have a single query string, we pass a list. To specify how many items to retrieve, we can use the nResults parameter. Here's what's returned. It's not the simplest format, so let's break it down. First of all, it's a dictionary. It has entries for IDs, the IDs of the returned items, embeddings, documents, metadatas, and distances of the query results. The embeddings entry is empty, simply because Chroma doesn't return them by default. Aside from this, each of these entries has the same format. Let's look at IDs. IDs contain a list of lists. The reason for this is that the query method accepts a list of query text, meaning we could use multiple query texts. We just happened to use one. Therefore, the results follow the same structure. The first list is the result of the first query. If we had multiple query texts, we would get back as many lists. As we can see, this is the same for each entry. They all contain a list of lists. Since we only used a single query text, we are only looking at the first list, the list for the first query text. In this list, we find a format similar to the parameters of the add method. The first ID corresponds to the first document, metadata, and distances. Next, let's see how to update a collection. Items in a collection can be updated with the update method. The syntax is similar to collection.add. In this example, we'll update the text for items ID1 and ID2. Once again, Chroma will take care of creating the embeddings using the collection's embedding function. Alternatively, if we are not sure the IDs are already present in the collection, use the upsert method. Upsert will add the IDs to the collection if they aren't present, and update them if they are, a combination of the update and add methods. Similarly, we can delete from a collection using the collection.delete method and specifying the IDs of the items to remove. Finally, if we want to completely empty the whole database, that means all collections and items, you can use client.reset. Hi again! In this final lesson, we'll take a look at more advanced ways to use Chroma by performing multiple queries and filtering with metadatas. Let's dive in. In the previous chapter, we used embeddings to make recommendations based on multiple data points. Let's do the same with the Netflix dataset and Chroma. will recommend movies related to other titles that a user has seen. Let's assume a user has seen Terrifier, which is a horror film, and Strawberry Shortcake Berry Bitty Adventures, a kids' TV show. It's an odd combination, but hopefully it will help differentiate the recommendations. Similarly to our previous implementation, we'll use the embedded text of the reference items as queries. First, we are using collection.get to retrieve both of our reference text. Notice that we are only extracting and storing the documents from these items in reference text. Since collection.query supports multiple query text, we can pass our reference text directly. We'll ask for 3 results. With multiple query text, we still get back a single dictionary. The difference is that we now get back multiple lists inside each entries list. Looking at documents, for instance, we see a first list that matches our horror movie and a second list that seems to match the children's title. Even though we asked for 3 results, we're getting 6, 3 for each query text. Notice how the titles we used in the query were most highly recommended, which makes sense as they are the most similar to the query. These could be removed in post-processing by extracting the documents from the documents key and filtering out documents that are also in the reference text. Another great way of filtering results is by utilizing metadata. So far, we've only worked with the IDs and documents from the Netflix titles CSV. But additional information, like the type, whether the title is a film or a TV show, and release year is also available. This data could be very useful if, for example, we only wanted to recommend films released recently. We've edited the code to load the CSV by creating a list to store the metadatas and populating it with the type and release year from each row of the file, stored together in a dictionary. Like before, we also create a list of IDs so we can add the metadatas to the existing items. We can update the items with their metadatas using the update method, this time specifying the metadatas argument. We can now use metadatas to filter our query. We are going to make the same search as before, but we'll include a where clause to indicate we only want to retrieve items where the type metadata is movie. The where filter we used here is actually a shortcut to mean equals, which we can define explicitly using another dictionary with the $EQ key. There are a few operators we can use to support different comparisons, including greater, less than, and not equal to. Finally, where filters can be combined with logical operators. In our case, we want titles of type movie and released after a certain year. To do this, we combined 2 where filters with an AND operator, type equals movie and release year greater than 2020. To filter for results that meet at least one condition, we can use OR instead of AND. There we have it. Our recommendations now only include movies released after 2020. Congratulations on making it to the end of the course. Let's recap what you've learned and finish with some resources to continue your learning journey. In Chapter 1, you learned that embeddings are vector, or numerical representations of text that capture its semantic meaning. You used OpenAI's embedding model to create these vector representations and computed the cosine distance to compare the similarity between texts. This unlocked applications like semantic search and recommendation engines that could relate text by their semantic meaning. In Chapter 2, you began using the OpenAI embedding model to enable real-world use case, including semantic search and recommendation engines. You also saw how embeddings can be used for classification tasks, including sentiment analysis and categorization. Finally, in Chapter 3, you took a big step toward creating a production system by learning about vector databases. You learned how to use Chroma to embed, store, update, and query vectors in a more reproducible and efficient way. So what's next? Luckily, DataCamp has a ton of resources for you to continue your journey. For enterprise companies with more funds or startups looking to move quickly to capture demand, a cloud-based managed vector database could be a good option. Two of the most popular are Pinecone and Weaviate, and you can learn about both right here on DataCamp. For many AI applications, including chatbots, embeddings and vector databases are only a part of a larger system, which may also include large language models or LLMs. LangChain is a great framework to tie all of these pieces together under a single unified syntax, so check out these resources if you're interested in learning more. Congratulations again! Best of luck on the rest of your learning journey.